How many of you are familiar with the classic problem, the Towers of Hanoi? Towers of Hanoi. Raise your hand if you're familiar with it. This one? So just a couple people? All right, it's a very simple problem. I'll show you what the problem is, and I'll show you the recursive solution, and then we'll do a quick analysis of the recurrence. So the idea is this. You have some disks, like flat disks. You ever have something like this? A child, sometimes we give them something like this when they're small, and they put like a disc on it, and then a smaller disc, right? And they try to make a stack from the biggest to the smallest, right? Have you seen that before? Okay. So what we're going to so these things, we're going to call these things pegs. So peg, 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 and then we can take a disc. So what we're going to do is we're going to start and put one disc on the peg. And we're going to call this A, we're going to call this B, call this C. Sometimes we can call this the start, because we always start from this one, because we've got to start somewhere. And then we call this one the end, because we want to make all the pegs, all the discs from here move to the end. And this is an extra one, so we're going to call it AUX. What it stands for? Auxiliary, right? Auxiliary means extra one. Okay, so the idea is we want to pick up one disc at a time and move from the start peg to the end peg. So you can see how many moves do I need to do to accomplish that. How many moves do I need to do to go from here to here? One move. Okay, so that's easy. Now let's just analyze what we did. What we moved is we moved a disc from the start to the end. But if we wanted to, I could take auxiliary and end and swap them, and I could just as easily, with the same amount of work, move from start to auxiliary. So I can move one disc to auxiliary with one move. Or one disc to end with one move. Now what happens when I add more discs? So what I'm going to do is I'm going to add a secondary disc. This disc is a little bit smaller. And the rules, now that we have two discs, the rules are going to be important. The rules are you always have to have discs cannot be bigger on top than on the bottom. So no disc higher can be bigger than any disc lower. So I cannot take these two and have them like this upside down. I cannot move this one here and then move the big one on top of it. So with that rule, I'm going to ask you to recall how we solved 1. Because the disc on the bottom is the biggest, if I only look at the discs other than the biggest disc, essentially you can say the pegs are all empty. Because the biggest disc is never going to get in the way of anything. Because it's always the biggest, so it'll never be a problem. So therefore, I can solve the problem of one disc, this one right here, to move it from here to the end in one move, or from here to auxiliary with one move. So I'm going to move from here to here in one move. So therefore, solving the problem for 2, I'm going to solve the problem with the discs on top of the biggest one with a complexity move of one move. So once I move this all over here to the auxiliary, I'll move the big one from here to the end. And then all I need to do is to put whatever was on top of the biggest one back on top of the biggest one, which means I'm going to take this one on top and put it here. How many moves is that total? 3. 3 moves. So it's going to be 1, 2, 3. So let's see what we accomplished. We accomplished moving 2 discs from one peg to another peg. Right? Now, if we add 3 discs, then we can think of the bottom disc, again, as the biggest disc. And again, if we just consider it as the biggest disc so it doesn't get in the way of everything above it, we can solve the problem of moving these 2 onto the auxiliary in how many moves?
2.
No. 3 moves. Right? Forget about the biggest one. The 2 to move here, we can solve it in 3 moves, which is going to be this one. Little, medium, little. So the same as we did for 2, this is 3, but we're moving 2 above the big one. So it's going to take us 3 moves to move these 2 off to auxiliary. Then I will move the big one into place. Then I have to move these 2 here. How many more moves? 3. So the little one, the medium one, here. So 3. So basically, it takes me how many total moves? 3, 1, 3. So you see what we had? So we had before, we had 1, 1, 1. Now we have 3, 1, 3. And before we had really 0, 1, 0. Where this is moving the disks above the bottom disk out of the way. Well, when you only had one disk, then 0 above it. When you have 1 above, so it took you one move to move 1 out of the way, then you move the big one. I call this the big one. Move the big one, and then you move the other ones back to where they belong. So now you can see what's going to happen is effectively it's taking us 1, 3, and 7. So now it takes us 7 moves to move 3 disks from here to an arbitrary location. So therefore, if I have 4 disks, I have to move 3 of them out of the way. And to move 3 disks is going to cost me what? How many moves? 7. Which is 15. So you can see what's going on. Now, so it will take me 15 moves to move 4 disks, following the rules of moving 1 disk at a time and never having a bigger one on top of any smaller one, on any stack, or any peg, whatever you want to think of it. So this procedure essentially can be written in code or in an algorithmic way of saying, if you want to solve this problem, which is called the Towers of Hanoi, if you want to solve the Towers of Hanoi for n disks, like 6 disks, 5 disks, whatever, then you have to solve it for 1 less than that to get them out of the way, then move the 1, and then move the n minus 1 on top of the biggest one. So what we've done essentially is take that logic that we've demonstrated here, and we put that logic in this algorithm. So the procedure or the logic or the function of Hanoi to move n disks from here to here using this auxiliary, if n is more than 0, if you want to move more than 1 disk, more than 0 disks, then move 1 less than that from the from to the aux. Meaning, if we're solving it for 2 disks, you're going to move 1 from the from to the aux. Then you're going to move 1 from the from to the 2. Then you're going to move the 1 from the aux onto the 2, and you're done. If you're going to have 3 disks, if n is coming in as 3, then you're going to move 2 from the from to the aux. But that's a recursive call. That's going to be 2 from to aux. And that means I'm going to now move what? 2 from the from to the 2. So it's going to recurse and it's going to ultimately solve the problem. Okay, so this is the code for Towers of Hanoi. Let's analyze this code. What exactly are we doing? Well, basically, there is the concept of actual work and recurrent work. Actual work and recursive work. Actual work, what do you actually do? Well, if you look at the algorithm, the only thing we're actually doing, recursing, the only thing we're actually doing is writing or moving a disk. When we say write, it really means move the disk. Move 1 disk. So how many moves are we making? We're making 1 move, and then we're making 2 recursions. So therefore, our complexity can be written as, if you have 0 disks to move, then n greater than 0 is false, and therefore you do 0 moves, 0 writes. So T of 0 is 0, because if you're trying to move 0 disks out of the way, then you have nothing to do and you're done. Okay. If, however, your value of n is not 0, but it's higher, greater than 0, then you are going to have to do 1, and this 1 is your move. 1 operation, and then you're going to recurse with n minus 1, and then you're going to recurse again with n minus 1. So it's going to be T of n minus 1 plus T of n minus 1, but we can say, hey, this is the same as this, so it's basically 2 times T of n minus 1 plus 1. So the recurrence is set. T of n is equal to 2 times T of n minus 1 plus 1. And that's what it is right here. So now what we're going to do is we're going to say we're going to expand our substitutions. We're going to try to do this 3 times and see if we can generalize it. So T of n minus 1 is here, And all we're doing here is substituting n minus 1 for n. So it's going to be t of n minus 1 is going to be 2 times t of n minus 1 minus 1, n minus 2 plus 1. And that gives us the second expansion. If we want to solve for t of n minus 2, then solve it by putting n minus 2 for n. So it's n minus 2 minus 1, n minus 3. And you can see dot, 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 the expansion. So let's see what happens as we try to put, oops, sorry about that. Let's see what happens as we try to put these together. So this is original. This is one expansion. Then I'm expanding this to here. That's the second expansion. And then I'm going to take this and I'm going to make this a third expansion. So this is the third expansion. This is the second expansion. Okay? So this is the third expansion, second expansion, and first expansion. Everybody understand? So now that we've done this, substituted 3 times, let's see what we have. But in order to simplify this, notice there's multiplications here and brackets and parentheses. So you can see this is 2 times t of n minus 3 plus 1, but when you multiply this by 2, you get 2 squared. You get 2 to the 1. And when you multiply 2 by 2 squared, you get 2 to the third. Okay? 2 to the 1 by 2 is going to be 2 squared. 2 times 1 is going to be 2 times 2 to the 0, which is going to be 2. And then plus 1 is 2 to the 0. So we expanded 3 times, and then we collected and simplified our expression to see what's going to happen. And what's happening here is that we see that what we have is 2 to the third, t of n minus 3, and then 2 squared plus 2 to the 1, 2 to the 0. So what do you think we would have if we repeated 4 times? What would that be? 2 to the 4th, t of n minus 4, 2 to the 3, to the 2, 2 to the 1, 2 to the 0. So what we're getting basically is we are getting 2 to the I in general, t of n minus I, because same number, but this exponent is not I, it is I minus 1, it's 1 less. So what we have is 2 to the I, t of n minus I, plus the summation, or the sum, of 2 to the 0, 2 to the 1, 2 to the 2, tick, 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 2 to the I minus 2, 2 to the I minus 1. Add those together. And so basically, because we are able to put anything into I, because I is simply a number of substitutions. If we make lots of substitutions, I can be a big number. We will always choose a substitution for I that will bring us back to our base recurrence, which is t of 0 is equal to 0. So in order for this to get t of 0, what does I have to be? I have to also be n. So therefore, when I is equal to n, it's going to be t of n minus n, t of 0, which is 0. And 2 to the n times 0 is 0. So that whole term disappears. So all we have left is the values of the summation here when I is n. And of course, when I is n, this becomes n minus 1, n minus 2. So it's the summation of 2 to the 0, 2 to the 1, 2 to the 2, all the way to 2 to the n minus 1. That's the summation, right? So it's the summation as I goes from 0 to the I of n minus 1. Does everybody understand that? Any questions on that? No? No questions? Okay. So if there's no questions, so we have to solve the summation. Now this summation, we're going to look at that in a little more detail later, but basically we can solve this type of summation by what we call a geometric series. And the geometric series says the sum of these n terms is a, which is the first term, minus the first term times the ratio to the number of terms over 1 minus r. Now, let me make it very, very clear to what we're doing. So it's very, very clear to you. Okay? So, the sum that we're trying to add, the first term, the smallest one, is 2 to the 0, which is 1. So it's going to be 1 plus 2 to the 1, which is 2, right? Plus 2 to the 2, which is 4, plus 2 to the 3, which is 8, all the way to 2 to the n minus 1, correct? Now, this is the first term, so that's a. Now, how many times a gives us the next term? How about if I multiply this one by 2, I get? How about this one by 2, I get? Okay, so that means to get from a term to the next term, all you have to do is multiply the previous term by 2. That's called a ratio. So R, the ratio, is equal to 2. Okay, now, how many terms do we have? Well, the first term is 2 to the 0, then we have 2 to the 1, all the way 2 to the n minus 1. So clearly, 1 to n minus 1 inclusive is n minus 1. Plus 1 is n. So the number of terms is n. So in order to solve the sum of these elements, all we need to do is take the first term, and the first term is equal to? First term is equal to 1 minus 1 times the ratio, which is 2, to the number of terms, which is n, over 1 minus the ratio. So this is going to be 1 minus 2 to the n over 1 minus 2, which is minus 1. So what I'm going to do is I'm going to multiply top and bottom by minus 1 over minus 1, because that's the same as 1, and that's going to change our value to what? To 2. 2 to the n will be positive minus 1. That's it right there. Are you with me? So our solution to the recurrence is 2 to the n minus 1. What does it mean? It means that if you have n disks to move, according to our algorithm, it will take you this many moves. For example, if you have 10 disks, if n is 10, it will be 2 to the 10th minus 1, that's 1,023. If you have 20 disks, it'll be 2 to the 20th minus 1, which will be 1 meg minus 1. If you have 30 disks, it will be 1 gig minus 1. Okay? There was an ancient belief in Vietnam, where Hanoi is from, is that if you solve the towers of Hanoi for 64 disks, it will be the end of the world. And actually, they might have been right. Because 64 is quite a big number. Basically, if you have 64 disks, the number of moves it'll take to solve it is going to be 2 to the 64th minus 1, which is equal to 2 to the 20th times 2 to the 20th times 2 to the 20th times 16, which is 2 to the 4th, right? Now 2 to the 20th is more than a million. It's a meg, right? So it's a million times a million. That's a trillion. So this is really a million trillion times 16.
16 trillion.
So how fast can you move these disks without a mistake? Computers can do it without a mistake. Now, if I start my computer on n is equal to 64, if I start my computer at n equal to 64, and I go to lunch, is it going to be finished? No. It's not going to be finished because even if it makes 1 million moves per second, it's still going to take an exponential number of centuries to solve the problem. So that tells you this algorithm has a very high, what? Complexity. It doesn't mean it's going to take a long time. High complexity. Well, isn't that the same thing? No. Because if you solve Towers of Hanoi for 5 disks, that's only going to take 31 moves. That's not a long time. But 40 disks might take you a week. That's a long time. And 60 disks till the end of time. That's a long time. So complexity is not whether it's fast or slow. Basically, an algorithm with high complexity will take an extremely long time to solve problems of a big size. So when the problem is big, it will take super long to solve it. Complex algorithms with very small problems can solve them fairly quickly. But when the problem size increases, exponential does what? This. That's an exponential curve. So that's the problem. So Towers of Hanoi is an exponential complex problem. The number of moves is an exponential function of n, specifically 2 to the n. Okay, minus 1. But who cares about -1 when you're talking about a million times a trillion? -1? Doesn't make much of a difference to me. Okay, any questions on that? All right, good. Let's look at the case of binary search and let's solve this algorithm. So the idea of a binary search, here's the code. Very, very simple idea. We are going to search an array called R, which is indexed from little a to little b, low index, high index. We're searching for element X, which is our key. So the first thing we do is remember how we work. If A is less than B, we have at least 2 elements. If A is equal to B, we have 1 element. If A is bigger than B, we have no elements. Low index, A, high index, B. So therefore, our recursive binary search says if A is bigger than B, then there's no what? No elements, therefore search returns false. Else, it means this says you don't have elements. This one says you have at least 1 element. So therefore, compute the middle index of first plus last divided by 2. Find the middle value. If you have 1, A plus B div 2 is going to be the same thing. If you have more, it's going to be towards the middle. Okay? So, find that middle index. If X matches the middle index, return true. Well, that's correct, because if it matches it, we've seen this before, if it matches it, we should return true, because we're searching for it. But if we don't return true, it means that it's not a match in the middle. Well, if it's not a match in the middle location, and our array is assumed to be sorted, then if the value we're searching for is less than this middle, then we should only search to the left of that. But if the value we're searching for is bigger than this one, then we should only search from the right-hand side. So therefore, we're going to bin search. If X is smaller than the middle, then search the array from the beginning, 1 left of the middle for X. But if it's not less than the middle, so it must be more than the middle, then search mid 1 to the right all the way to the end. Make sense? So, let's see how that would work. Let's say I have 7 elements to search. 7 elements. 0 to 6 indexed. What's 0 plus 6 div 2? 3. 0, 1, 2, 3, 4, 5, 6. Now I'm going to check the element. It's not a match. So it's either going to be less for the lesser 3 or more the upper 3. So let's say it's going to be the upper 3. What's my index is going to be? 4, 5, 6. Recursively I put in 4, 5, 6 searching for X. Now I'm going to say what's 4 plus 6 div 2? 4, 5, 6. It's not a match. If it's not a match, it's either going to be less than this, so it's element at index 4, or if it's bigger than that, it could only be the element at index 6. Let's say it's less than that. So A is 4 and B is also 4. Because M was 5, so we want to go to the left, so that means we decrease the value of L by M minus 1, so that means they're both the same. We have 1 element, we're going recursively of 4 and 4. Condition is false, A greater than B false, they're both 4 and 4, so we have at least 1 element. What is 4 plus 4 div 2? So at that point we add, it's 4, is it a match? Well, if it's a match, we return true, but if it's not a match, then the element must be to the left or the right. But there's only 1 element. But we don't know that because we're kind of dumb, so we don't know that. So we're going to say, okay, if it's to the left, then what happens is I want to search the left half. That means I want to keep the left bottom the same. I want to move the upper left. But that makes B less than A. If it's bigger than what I have, I want to do what? I want to have my low go to M plus 1 and leave my upper. In this case also, A goes bigger than B. So basically, once I test the last element, it's not a match. It's either going to be A or A. Either one is going to make A 1 higher than B. And what's going to happen then is when they go in, the condition will be what? The condition A greater than B will be true, and we will return false. Get the idea? Okay, so let's talk. Now, here's the issue. Notice that it was beautiful. 7, 1, 3, 3. 1, 1, 1, 1. That's because it was a perfect thing. If you have 7, it's a perfect way to take an element out and have 2 3s. If you have 3, it's a perfect way to take 1 out and have 2 1s. And then you have 1 and a 1. If you had 15, same thing. If you have 15, you have 7, 7, and a 1. You take 1 out, you get 7 or 7. And then you have 3, 1. If you have 31, perfect. 63, perfect. 1023, perfect. Life is not always perfect. I hate to break it to you. A lot of you probably thought it was, but now you know it's not true because I told you that. Right? And you believe everything I say. So, what if we had, for example, 10 elements? Or let's say we had 9 elements. So 9 elements, we'd have, let's say we index them 1 through 9. Or 0 through 8, makes no difference. 0 through 8. What's 0 plus 8 div 2? 4. 0, 1, 2, 3, 4. 5, 6, 7, 8. 4, 1, 4. Now let's say it's not a match. So the left side and the right side both have 4, which is an even number. So let's look at this one. 0, 1, 2, 3. What's 0 plus 3 div 2? 1. Div means integer division. You truncate any so that means I'm going to have 0, 1, 2, 3. So that means if I miss this one, I'm going to have 2 on the right, only 1 on the left. Why? Because it's even. Actually, any even number, when you don't miss it, you're going to have a mismatch. For example, let's say I had 100 elements. 0 plus 100 div 2 is 50, right? 50. 0 through 49 is 50. Here's the element in the middle, and then I'm going to get 49. So if this is not a match, I'm going to go 49 on the right, but 50 on the left. So whenever you have an even number, you never have an even split. Whenever you have an odd number, you take it out, you have an even split. So for the sake of analysis, it's easier to think about odd numbers, but when do we always have an odd number? I mean, we could see 9, take 1 out, you get 4 and 4. But 7, you take 1 and you have 3 and 3. 3, take 1 out, you have 1 and 1. 15, take 1 out, you get 7, 7. 31, you have 15, 7, 3, 1. So 2 to the power minus 1 is a perfect number that allows you to always stay odd whenever you take the middle element out. The 2 halves are odd. So what we have here is the total number of elements is going to be considered to be 2 to the k minus 1, like 7, which is 2 to the third, or 15, which is 2 to the fourth, minus 1. So what we're going to do is we're going to say t of 0 is equal to 0, meaning binary searching 0 elements is 0 comparison elements, because our characteristic operation is a comparison. So if you have 0 elements, if it's no search space, if there's nothing to search, return false, never do a characteristic operation. So if your search space, if n is 0, then you don't do any of this, therefore t of 0 is 0. T of 1, t of n rather, when n is not equal to 0, when it's bigger value, is going to equal to 1 if it's a match. Because think about it. Let's say I have 1,000,000 elements. So that's false. Calculate the middle. Find the middle element. If it's a match, you only did one comparison, you're done. So t of n is equal to 1 if it's a match. But if it's not a match, it's going to be compare and then go deeper. Left side or right side. And then where we're going to split it, we're going to say t of n plus 1 over 2 minus 1. And n minus n plus 1 over 2 minus 1. What we're going to do is we're going to split the differences unevenly. Notice that these two expressions are very close to be the same. This is n plus 1 over 2. It's about half of n minus 1. And this is half of n minus 1, taken away from n, which is half of n. So these are almost the same. In fact, they are very, very close. They'll only be off by 1 at most. And because they'll only be off by 1, what we're going to do is we're going to assume that we can simplify our analysis by always assuming that the size of the array is in this form. And that gives us this powerful way to split, which looks like this. So it looks like this. So what we're going to get 2 to the n minus 1 can be split into 3 parts. One middle element, and then 2 to the n minus 1 minus 1, and 2 to the n minus 1 minus 1. So if we do that, if we start our analysis here, then both the left and the right will be about the same or exactly the same, so we can just say 2 times that. Compare plus 2 times that. And that makes our analysis a lot easier than trying to go even, odd, odd, even, all the possibilities. Actually, the results are exactly the same, so it doesn't matter. It doesn't really matter. Okay, so now what we have is we have t of 0 is still equal to 0, so we're always going to assume that n is in the format of 2 to the n minus 1. So t of 0 is still 0 because there's no comparisons on an empty array. T of 2 to the k minus 1 is 1 if it's a match, but if it's not a match, it's going to be 1 plus t of 2 to the k minus 1 minus 1, which is either the left side or the right side. Notice that we don't have to do this one and this one. Why not? Because we never do the left side and the right side, because the array is sorted. Once we make a comparison, we go left or we go right. We never look back. So therefore, that's our complexity. So the best case, of course, b of n is equal to 1. For example, if the middle element is true the very first time, that's your best case. That's great. Not very likely, but that's what will happen. Now the worst case occurs if the comparison is always false. And the worst case occurs when the element is never in the array. We never find it. So if it's always false, it's going to be the worst case. Now, worst case of 0 is 0. Even if you never find it, if there's no array, no work, because you never have to compare, because the condition will always be true initially, you'll never compare. But the worst case of this is going to be 1, which is your comparison, plus the worst case of the left or the right half. Do you remember? No.
Always forget.
I know. Don't worry, it's only my life. Alright. So now what we have to do is we have to solve this. Notice that we went from B to W. We didn't consider what? We went to look at the best case, worst case. We didn't consider average case yet. So the worst case is going to be W of n, where n is this format. 1 plus W of this. Everybody understand how we got this? No. Actual work, actual comparison, plus the recursive cost of the left side or the right side. So now what we're going to do is we're going to replace this one. When k is equal to k minus 1. When k is equal to k minus 1, it's going to be k minus 1, k minus 1 minus 1, k minus 2 minus 1. And then we're going to go here, and we're going to substitute this one for w of 2 to the k minus 2 minus 1, and that's going to be 1 plus w of 2. Okay, so you see what we have. We have 1 plus 1 plus 1 plus this. So it's a very easy recurrence. And when we do this I times, you can see we did it 3 times. We have 1 plus 1 plus 1. So we're going to have, when we do it I times, we're going to get I. Plus w of k minus 3 becomes w of 2 to the k minus I minus 1. Now, what we want is we want the value of 2 to the k minus 1 minus 1. We want this expression to equal what? We want that to equal what? Zero. So therefore, what we're going to do is, when is this equal to 0? 2 to the k minus 1 minus 1 is equal to 0 when 2 to the k is equal to 1. When 2 to the k equals 1, 1 minus 1 makes 0. So when is 2 to the k equal to? So when is the value of 2 to the k minus 1? For which value of k is it equal? 0. So that, because 2 to the 0 is 1 minus 1, is going to be 1 minus 1 is 0. W 0 is equal to 0. So therefore, we're going to have w of 2 to the k minus 1 is equal to k plus 0, which is equal to k. So we have a solution, which is equal to k. But what the heck is k? Well, k is not a really interesting number for us. It's a useful number for us, not really interesting. What we have, we go right here. Okay, so remember we started our analysis, we basically said n is equal to 2 to the k minus 1. We liked that because it was easy to take one element out and have two left and right even halves, right? So, in order to find out, and then we found out in our analysis that the number of characteristic operation is k. But k is not a function of n. Well, it is, but we want to know what our answer in terms of n, not in terms of k. So therefore, we're going to rewrite this by adding 1 to both sides. We're going to get n plus 1 is equal to 2 to the k, right? Yeah. And now we want to solve for k. To solve for k, 2 to the k, how do we make the k drop out? We take the inverse function of the exponential 2, which is log base 2. So we take log base 2 of 2 to the k is equal to log base 2 of n plus 1. 2 to what power is 2 to the k? K. So this is just equal to k is equal to log base 2 of n plus 1. Now log base 2 is a logarithmic function. That's a function that grows like this. It goes basically like this. Right? Slowly or quickly? Very slowly. So log 2 of n plus 1 is very similar to log 2 of n, right? Anybody know what that graph looks like? This is the log of L. By the way, this is, you can also write Lg of n plus 1. You understand that, right? Lg is log base 2? Okay, so what I'm saying is this graph is Lgn. What does the graph of Lgn plus 1 look like? Anybody know?
Right shift, left shift by 1?
Left shift by 1. So we're going to do over here. And so what we're going to do is we're going to basically get this. Very similar. Does it look very different or very similar? Very similar. As n gets bigger and bigger and bigger, these two are practically the same. Okay. Any questions? Okay. Now, the next analysis we're going to look at is going to do what we call the average case analysis. This one is the most interesting, but it's also more difficult than what we looked at before. So I want to make sure you understand what we're talking about and how we're getting this result. Here's my array. I'm doing a binary search. The best case is obvious. You look in the middle, you match, done. Is it realistic? Is it realistic best case is going to happen? Well, it's not very realistic. If, for example, let's say you have 1,023 elements. If you're looking for something in this sorted array, and each of them is equally likely to be the one, what's the probability that 1 out of 1,023 is a match? 1 out of 1,023, which is close to 1 out of 1,000, which is 1/10 of 1%. So the probability that this is going to be a match is very low. So the probability of this match is 1 out of 1,023. Now, imagine our array is 1,023, 1 out of 1,023. Now, if it's not a match, how big is the left side and the right side? Which is exactly 511. Because you're going to get 511, 511, and 1. So you have 2 to the 10th minus 1. You have 2 to the 9th minus 1, 2 to the 9th minus 1, 1. So, what's the probability? What's the probability that if you mismatch the first one, you match the second one? 1 over 511. Now I know that 511 is not a nice number. So what I'm going to do is I'm going to allow you to cheat. In the following way. Instead of saying 1 over 1023 for the first one, we're going to say 1 over 1024. So when we have 1024 elements, roughly speaking, the probability of the first one is 1 over 1024, right? The probability of the second one is roughly 1 out of 512, correct? So, so let me ask you a question. How often are we going to match the first element out of 1024? How often? Huh? 1 out of 1024 times. Right? Very, very rarely. So that means what's going to happen 1023 out of 1024 times? We're not going to match. So that means that, now how much is 1023 divided by 1024? The answer is we don't know. But the answer also is, I have a calculator and I'm very good at it. So I'm going to say 1023 divided by 1024, 0.9990234. I can get more decimal places if you're interested. But I'm not going to get it. So basically, the likelihood of mismatching the first element out of 1024 is almost certain, right? Highly likely that you'll mismatch. What's the probability that you'll mismatch the second element? Well, that's going to be equal to 511, right? Roughly divided by 512. 0.998. You might make it, but the probability is extremely high that you will not match it, either on this side or on that side. Why? That's the probability. So what we're going to do is we're going to use the idea of 1 over 2 to the k minus 1. That's the probability of matching, correct? But the probability of not matching is 1 minus 1 over 2 to the k minus 1. So when k is equal to 10, this is 1 over 1023. And this is 1 over 1023 when k is 10. And this is equal to 1022 out of 1023, correct? What is going to happen as we go from 1023 to 511 to 255 to 127 to 64? By the time we miss at 63, we're going to have 2 halves are going to be equal to what? 30? 31. 31. What's the probability of missing? 30 out of 31. What's the probability of making it? 1 out of 31. It's a 3% chance of making it, 97% chance you're going to keep going. From there, we're going to go to 15. What's the probability of missing it? 14 out of 15. What's the probability of making it? 1 out of 15. After 15, if you miss it, you're going to go to 7. 14% chance you'll make it. 86% chance you won't. 3, if you miss it. 33% chance you're going to make it. Assuming the element is there. Because if it's not there, you ain't making it. But if the element is actually there, you have 1 out of 3 chance of making it, 2 out of 3 you won't. You miss it. Now you have 1 element. You have a 100% chance of matching it if it's in there. 0 if it's not. So I will assume that the element is always there. Let's assume the element is always there. So probabilities can be easily computed. So P, probability of the element in the array, 1.0. Okay? So therefore, all we need to do is add all of the probability of missing. Because if you add all the probability of missing, you're going to get the average work that you're going to do. Because probability of missing is a comparison. So we have to simply add the probabilities of missing. So therefore, assuming the element is 100% certainly in the array, if we're searching an array of 1, then the probability is 100%. Are you with me? If, however, the number of elements is not 1, but it's some number like 3, 7, 15, 31, 2 to the k minus 1, then the probability is going to be the expectation of mismatching it, which is the comparison probability, plus the average complexity of the left half or the right half. So it is 1 minus this. So this is basically, again, think of 1,000, think of 10 as k. Then this is going to be 1 minus 1 over 1,023, which is 1,022 out of 1,023. So this is almost 1.0. By the time we get down to 3 elements, that comparison is only going to count as 2/3 of a comparison. And by the time we get to 1, that comparison will count as 1 comparison. So we will count all of the expected failures at the current level, plus recursively the expected failures at the recursive levels, where the half continues. So if we expand our terms, basically we want to substitute for this. And so when we substitute for this, we get this whole thing is a substitution for this. So it's going to be 1 over 2 to the k minus 1 minus 1. That's the expected number of, that's the expected probability of failure, plus the average complexity of the following half. This is this half, this is the following half. So now I'm going to take this one, I'm going to expand this one. When I expand this one, I get this plus this. So can I see a pattern of doing it? So I see I did it 3 times. 3 times. Notice it's that 2 to the k minus 3, k minus 0, k minus 1, k minus 2. So when we go to I, this is going to be k minus what? K minus I minus 1. K minus I minus 1. K minus I plus 1. Because I'm subtracting k minus 1. So it's minus k plus 1. Okay? It's very important to set it up exactly just like that. So it's correct. So what we have here is we have this summation. Repeating this so many times, we have 1 plus 2 to the k minus 1, 2 to the k minus 1 minus 1, 2 to the k minus 2 minus 1, and finally 2 to the k minus I minus 1 minus 1 plus a to the 2 to the k minus I minus 1. So now all we need to do is we need to solve this. So what we're going to have is we're going to get k minus 1. How do we get that? How do we get k minus 1? Well, look at our average analysis. Average of 1 is equal to 1, assuming the element is present, right? Average of 1 is equal to 1. So how do we make this equal to 1? When this is equal to 2. 2 minus 1 is 1. So when is 2 to the k minus I equal to 2? When k is equal to, I is equal to k minus 1. When I is equal to k minus 1, we have k minus 1, which is 2 to the 1, correct? Everybody got it?
Yep.
So we have to let I equal to k minus 1, and then this is going to be equal to 2 to the 1, which is 2 minus 1 is 2 to the 1. So 2 to the 1 is going to be 1. Minus the summation from 0 to k minus 2. K minus 2. of 2 to the k minus I minus 1, which gives us k, minus the summation. Now the summation, I'm not going to go through the details of this, but basically the summation, and on the next section we'll talk much more about some math ideas, but the summation here is going to be equal to, less than, this particular continuous summation, also known as the integral, which we'll talk about, but don't worry about it, don't sweat it out. Even if you don't know too much about it or you forgot it 3 years ago, don't worry about it. This is going to be less than this integral, which is approximately equal to this integral by taking the minus 1 out. And when we solve it, we ended up, and I'm just going to cut to the chase to get to the bottom, we end up having equal 1 over 2 natural log of 2 minus 1 over natural log of 2 times 2 to the LGN plus 1. Of course, this is nothing more than n plus 1. So this is going to be 1 over this, minus 1 over ln2, n plus 1. Combining both terms, we have this simplified expected value. So this value tells us what is the number of expected comparisons on average in binary search when the probability of the element in the array is certain and the likelihood of finding it is the same everywhere. So let's see if we can make some sense out of it. So for example, if n, for example, is equal to 1023, then 1023 plus 1 is 1024. LG of that is going to be what? 10. Minus 1 over 2 ln 2, which apparently is very close to 0.72. 0.7. So this 10 goes down to 9.3 plus 1 over natural log of 2n plus 1. So it looks like our average complexity is going to be this plus a small adjustment. Let's take a look at that. But before we take a look at that, let's see if we can... So this is the number of expected comparisons on binary search, assuming the element is 100% certain to be in the array, with the probability of finding it equally everywhere the same. Now, what is the probability? Let's say the probability is not certain now. So that means there must be... What happens when the element may not be... What happens when the element's not in the array? We're going to fail. What will be the complexity of the failure? The complexity of the failure will be the worst case. So in a sense, what we have, let's call this A of n. So A of n is equal to, right, LG n plus 1 minus 1 over 2 ln 2 plus 1 over ln 2 times n plus 1, right? By the way, what happens when n becomes very large? Then n plus 1 is very large, right? And ln 2 is going to be what? 0.8, 0.7. So what's going to happen to this term? When n becomes very large here, what happens to this whole term? It goes to 0. The bigger the n, the smaller this term is. But this one is a constant. So actually, it's very interesting to see, for big values of n, this term is irrelevant. So it's basically log of n plus 1 minus 0.7. What does it tell you about the average case? How does it compare to the best case, worst case? What's the worst case? Okay, do you remember what we did with our binary search? We cut the array in half. Take an element out, cut the array in half. Pretty much, right? How many times can you cut an array in half? 8. 4, 2, 1. So 8 can be cut into 3 times. How about 16?
8,
8, 4, 2, 1, 4 times. How about 32? 16, 8, 4, 2, 1. So how many times can you cut something in half? Log base 2 of the size of the number. So that tells me that the worst case is failure, 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 failure. Failure cut in half, 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 failure. No more halves. Done. So what's the complexity of the worst case? Log 2 of n is the worst case. But this tells you that the average case is almost the same. It's log n plus 1, which you know what that looks like, right? It's like the same curve for big N. Minus 0.7. Thank you. So that means when you're searching for about 1,000,000 elements, which is roughly 2 to the 20th power, what is the worst number of comparisons that you expect? 20. 20. Because 2 to the 20th, how many times can you cut it in half? 2, 19. 18, to the 18th, to the 17th, tick, 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 2 to the 0. So 2 to the 20th, 1,000,000, a meg, can be cut in half 20 times. So that means if you don't find the element in the array, you will have how many comparisons? 20. And they will all fail. Okay. But this one tells you, on the average, if you have 1,000,000 elements, which means, by the way, n is equal to about 19, right? No, not 19. N is equal to 1,000,000. Let's call it a meg. So let's call it a meg minus 1. A meg minus 1 plus 1 is a meg. What's LG of a meg? 20 minus 0.7. This tells you that the average case is almost the same as the
Worst case.
Okay. Wow. Do you understand what I'm... Okay. So now so now let's just put the bow on this little discussion. A bow. You know what I mean by a bow? Make it look pretty. All right. Put a bow on it. So what we're going to have, I would like to now have, oh, I forgot what I was doing here. So basically here, the W of n, roughly speaking, was LG of n, right? So what is the average cost of, average complexity of searching the array where the probability of the element being in the array or not is unknown? It is equal to P times A of n plus 1 minus P times W of n. Does that make sense? So P times the probability of assuming it's there times 1 minus P times the worst case, because the worst case is definitely not there, and here it is there with probability P. So the probability is equal to 100%. This is what? If P is 1.0, what's this term? 0. If P is 0.5, what's this? 0.5 worst case. So the probability is 0.5, you're going to get 50% of the average plus 50% of the worst case. Which is going to get you, it's going to buy you about 0.3 better. So what we have here is, we can simply show it like this. So P, this is nothing more than average cost. And this is plus 1 minus P times the worst cost. And just to show you what it looks like, oh, I don't have it here. Okay. Do I have it here? No, I don't. Okay, so basically the bottom line is, if you're searching 1,000,000 elements, the worst case complexity is 20, and the average case complexity is about 19. When you're searching 1,000,000,000 elements, the worst case complexity is 30, the average case is about 29. What's the probability of the best case using 1,000,000 elements? 1 in 1,000,000. So if you feel lucky, but really lucky, you're going to get the best case, but probably not. Okay, does anybody have any other questions so far? Okay, when we come back on Wednesday, we're going to be talking about solving homogeneous linear recurrences. So we're going to be talking about how to use different techniques of solving recurrences and recursive complexities. Okay, see you Wednesday.